Good morning! Welcome to another Wednesday. This is your fourth Wednesday of the semester. Fourth Wednesday. That means there are... I don't know what to tell you. There are technically 11 left. Good morning. Hello, Michael. I hope you guys are doing well, surviving. Where is everybody today? Ooh, get some foreign music. Let's change this. Go find some... there we go. See how many people we have online here today. Twitch. Twitch tells me there's 12 of you. Good morning, Schwartzmeyer. What do you guys do during lecture? You guys legitimately pay attention? You guys eat lunch? You zone out. During my 199 lecture last week, or last semester, students, I'm pretty sure, would play video games during lecture. But, I mean, that was seminar. It's different. Seminar's different. It's just a different feel, different set of material. This is a little more concrete. Lunch or notes. Breakfast, solid. I wish I could eat lunch during lecture. It's kind of hard to eat and talk at the same time, though. Hopefully it's entertaining enough. For this homework, make sure it works with any general solution. How can we do this? You test it with lots of different values. So, ooh, that sounds like fun. MATLAB only gives you one set of values, but that's because you're only giving it one set of values. So change it. So in MATLAB Grader, it has that box below that tests your code. You can change that. That's just a second script file. So change the number of rows, change the number of columns, change the values. So change reshape. Take out reshape. Did I put that one in there? I don't remember putting in reshape. Maybe Dr. Ali put in reshape. I don't know, it's not my favorite function. I personally like to use rand_i. So just say rand_i 1010 or give it a bunch of yeah, here, let me tell you. Change it to this. That'll give you a random matrix with 5 rows, 7 columns. So if you change the 5 and 7, that changes the number of rows and columns you have. So use that line of code instead. Like I said, I don't remember putting in reshape. Dr. Ali probably did that. But just try it with a different set or create a matrix of your own. Change that little script file there, press run, see what happens, press run, see what happens. Yes. Watching TV, Travel Channel, ghost shows, and now I'm sitting watching this. It works. Okay, great. I'm glad it works. Isn't it so rewarding? You change something, you're like, yay, I figured it out! And then you think, I spent hours on this only to change that one thing. And anyway, I don't know. Okay, so welcome to lecture. It's good to see you guys. Let's go ahead and start. So I totally forgot to go through your guys' quizzes and responses on Monday. So I didn't have any feedback for you guys, but I went through them today, which is good. A lot of you guys had questions on like the syntax between parentheses and brackets, or just indexing. So I'm gonna go through, before we get to actual lecture, I'm gonna go through some stuff that you guys want to keep in mind for this material. There's a lot from week 3 material, that one that your homework's due tonight. There's a lot there. I could not at all go through everything that you guys can do in creating arrays and modifying everything in MATLAB. You've just got to play around with it. You've just got to try it. And that's what makes it difficult. So think about your debugging strategy is right click, highlight, see what one side looks like, see what another side looks like, and how do you combine them. Okay, so just some review things before we get into matrix math. So first things first, brackets are used to create a new array. So some of you guys mentioned clarifying when you use brackets versus when you use parentheses. Brackets, creating a new array. Brackets are also used in your function to group your outputs. But essentially, if you're creating a new array, you use brackets. Parentheses are a little bit more versatile. So parentheses, you can use them in a couple different ways. So you can use them to group together your math operations. So if you have 3 times pi divided by 2 times pi, obviously you can simplify that, but you can group together like your bottom and your top, saying do this operation first. That's the first way to use parentheses. We can also use parentheses to index an array. So where we say, hey, I don't want all of A, I only want part of A. So we would type the name of our matrix, whatever it is, and then open close parentheses and give it the locations we want to change or access, or the rows and columns. We can also send inputs to a function. So like the sign function, we would send it some data. And so there's a couple ways in which we use parentheses. But the key one for you guys is this one right here. For this week, we're really focusing on this new way to use parentheses by indexing. Okay, so you are creating arrays and modifying and changing and all of that fun stuff this week. As you guys are doing that, there's a couple questions you need to ask yourself. First question, are you creating a new array or are you changing an existing one? If you're creating a new array, you just type the name, parentheses or equals, open close, brackets, and then you just type in your values. You type in the values, something goes on your right-hand side. But your left-hand side is just your single variable. Keep in mind, commas, put things next to each other. Semicolons, stack things on top of each other. If you are putting things next to each other, you need to have the same number of rows. If you are putting things on top of each other, you need to have the same number of columns. And so once again, if you run into a dimension mismatch or concatenation error, just right-click something in MATLAB or highlight something in MATLAB, right-click, run selection, see what is happening. What happens when you type this? What are the individual pieces? What happens when you put them together? Does it match? That's the first thing. If you aren't creating a new array and you are modifying an existing one, then we have our syntax over here where we say A and then open close parentheses. That goes on our left-hand side. So if we are modifying, if we are changing something, it goes on our left-hand side. And then whatever goes on the right-hand side. But the key piece, name of the array, open close parentheses, and then you identify what you are wanting, or where you want to change things. So if you are modifying and changing something, you're asking, what do I want to modify and change? Am I modifying just one number? Am I modifying several numbers? Which locations, which rows, which columns? If it's a vector, you would just say A, and then you would put in open close brackets, and then identify which locations. You can do this as your default, where you do parentheses, and then you always have your brackets. It will work if it's a single number. It will work if it's more than one number. So if you're confused on when to use the brackets, when to use the parentheses, all that fun stuff, just by default, put in the brackets. A, parentheses, brackets. Inside those brackets, you're identifying multiple or one location. If you have a matrix, then you also identify the rows and columns. Once again, use your brackets. Which rows, which columns. So that's identifying where do you want to change things. Which locations, which rows, which columns. The right-hand side is what do you want to change it to? What do you want to store in those locations? You're asking, are these new numbers? If they're new numbers, you just type them in. If it's a scalar, that's fine. You just type in that value and it will copy itself into all of the locations. If it's a vector or a matrix of new values, then you would just create that vector or matrix of new values. Benny, if you're having difficulty remembering when to use brackets or not use brackets as your default. Type your name of your matrix, open close parentheses, inside brackets. Type the name, whatever, open close brackets, open close brackets. It will work if you have a single number. So if you're only doing 3, 4, it will work. If you're doing 1 to 3, 3 to 7, it will work. If you are doing colon, end, it will work. So if you're confused about when you should use the brackets, just use them by default. Even though a lot of times you don't necessarily need them. Like here, I don't technically need them. But if you're having trouble remembering when to use them as default. Okay, so once again, right-hand side. So if it's a scalar number, it will just copy into all locations. You can also just create a new vector with new values. Open close brackets creates a new array. Or asking, do they come from another array? So this says, do they come from another array? If they come from another array, then you would just do something like this. A, open close, whatever, and then just a different array, same thing. It doesn't matter where these numbers come from, just as long as they're a valid set of numbers. So it can be a single number, it can be completely newly created numbers, or it can be numbers within a pre-existing array. Once again, identifying the locations or the rows and columns. Keep in mind, do you have one value per location? Scalar as an exception. So if you're indexing, if you're changing 3 locations over here, do you have 3 numbers over here? So those are some key pieces to keep in mind as you guys continue through your homework. Someone, who was it? Benny, there you go, Benny. Benny also mentioned, like, how do you test it with different sets of numbers? So you can change the MATLAB code in MATLAB Grader to test your function with different numbers. You can also test it in MATLAB itself. You can also test it on paper. So a lot of times I like to use paper to help me identify what's happening. So for example, for homework 3, problem 3, it's the corners function. Let's say you have a different array. So there's a 3 by 3 matrix given to you with n is 2. But let's say A is something different. Let's say A looks like this. It's a 6 by 5, 6 rows, 5 columns. So, and then ask, what if we had different values for n? What if n was 2? If n was 2, I want this array, this array, this array, and this array. That means I'm talking about this first one here is locations 1 to 2, 1 to 2. Rows 1 and 2, columns 1 and 2. And let's do this one. For this one, it's going to be rows 5 and 6, columns 4 and 5. Okay, so, and then I can do it for the other ones as well, but I'm just going to do with those, start with those two as an example. So let's say n was different. Let's say n was different. Let's say n was 3. If n was 3, then I'm looking at this one, these arrays. That one, this one, and this one. Okay, so this now would be 1 to 3, 1 to 3. This one now would be 4 to 6, and 3 to 5. Yeah. Okay, now let's change it again. Let's say n was 4. Then I'm looking at this one, this one, this one, and this one. Sorry. That means for my first one here, A would be 1 to 4, 1 to 4. And then this one here, it would be rows 3 to 6, columns 2 to 5. And then you ask yourself, how does it differ? So if I look at these indexes, it's 1 to 2, 1 to 3, 1 to 4. What if n was 2? What if n was 3? What if n was 4? How does that change by n? If I look at this one here, if n is 2, it's 5 to 6, 4 to 6, 3 to 6, 4 to 5, 3 to 5, 2 to 5. 6 doesn't change. 5 doesn't change. What can I use instead of that? How does this number change with respect to n? So just start with an example and try and figure out, okay, what if I changed it? How does my number change? How do I need to adjust my calculations? What if it changed to this? Does my adjusted calculations match that one? Okay, so sometimes it helps to write down on paper what you're trying to do. And we will get to this later on as well when we get to loops. It's crucial that you know how to write things down on paper so that we can help construct things and figure out what is the pattern, which is a weird word when you say it like that. Okay, took longer than I wanted to, but hopefully that helps. Hopefully that clarifies things, makes sense. Sorry for not talking about it on Monday. I just plain forgot. Okay, let's get into the material for today. So on Monday, we went through so many math operations. We went through matrix addition, subtraction, multiplication, element by element operations. So keep in mind that the asterisk is matrix multiplication. The dot asterisk is element by element multiplication. The dot divide is element by element division, and the dot exponentiation is element by element exponentiation. The regular caret is matrix multiplication. It's a derivative of matrix multiplication, and we will find out today that regular divide and left divide and right divide both also are a derivative of matrix multiplication. Okay, so be very careful with what you're trying to do. Do you want to do element by element? These are your options. Do you want to do matrix multiplication and its various forms? And these are your options. Okay, so today we're going to talk about matrix division. And I'm going to tell you that it's not really division. It's, once again, a derivative of matrix multiplication. And so you can't divide matrices. Instead of dividing matrices, we are going to multiply by the inverse. So if you look at the number 5, its inverse is 1 over 5. So if I take 3 divided by 5, I'm essentially taking 3 times the inverse of 5. That's the way that we approach matrix multiplication or matrix division without going into a lot of the details behind it. Okay, so let's look at some examples. Let's say that m looks like this and n looks like this. Before we get into calculating the inverse, I need to introduce the idea of the identity matrix. The identity matrix is just a square matrix that with ones along the diagonal and then zeros everywhere else. So here's the identity matrix of the 4x4. So if I say I2, this is how you would create the identity matrix in MATLAB. it would just be the 2 by 2 identity matrix, where there's ones along the diagonal and zeros everywhere else. So if I did m times I, m looks like this: 5, -2, 1, -3, 1, 0, 0, 1. If I did matrix multiplication between these two matrices, I have a 2 by 2 and a 2 by 2. My inner dimensions match. That's good. My result is going to be my outer dimensions, or a 2 by 2. So a 2 by 2 has 4 locations, so I need to do 4 dot products. So the first one, dot product between row 1, column 1. So it's 5 times 1 plus 1 times 0. Then I have row 1, column 2. So 5 times 0 plus 1 times 1. And then row 2, column 1, -2 times 1 plus -3 times 0. And then row 2, column 2, -2 times 0 plus 3 times 1. I do want to point out, I did 2 more examples for matrix multiplication in a separate video. I linked that video under the lecture information on UB Learns. So you can go straight to UB Learns under week 4 lecture information. There's a link to a matrix multiplication video that's like 6 minutes long. And I just go through 2 more examples that's very much more directed. So if you're looking for more matrix multiplication examples, you can go there and you can see how those problems are worked out. Because it's very crucial you know how to do that. Okay, so if I actually solve this, I get 5, 1, -2, -3. And if you notice, this is the same as, oops, too far. This is the same as m. So if I take a matrix times the identity, I get my original matrix back. It's essentially equivalent to 1. If I take A times 1, I get A back. Same idea. And that is what the identity matrix is. Okay, so let's get into calculating the inverse. So the inverse is a matrix such that if I take m times its inverse, I get identity. Or other way around, it's the inverse times a matrix, I get identity. So that's why we need to know what identity is because it informs us essentially that a number times its inverse or a matrix times its inverse gives me identity. The way we calculate identity is using this formula. M inverse equals 1 over the determinant of m times m adjoint or adjugate. That's our formula. We are going to focus this week on 2 by 2 matrices by hand. You can always do this in MATLAB with bigger matrices. Okay, so here is my equation. So that means I need to find the determinant and I need to find the adjoint matrix or the adjugate matrix. So first thing, find the determinant of m. For a 2 by 2, the determinant of m is pretty simple. So m looks like this: 5, 1, -2, -3. The determinant is just going to be by multiplying these elements along this diagonal, multiplying these elements along this diagonal, and subtracting. I like to draw a little fish to remind me I'm going to take these numbers minus these numbers. So I'm going to get 5 times -3 minus -2 times 1. 5 times -3 minus -2 times 1. And that's why I draw my little fish. And then you just add all that up. So -15 plus 2, -13. There we go. There's my determinant. Once I find my determinant, I keep moving forward. Keep in mind, in order for this equation to work, every value of the determinant will work except for 0. So as long as m isn't 0, I'm fine. Because if I do 1 over 0, that gives me infinity and my math blows up. Okay, so as long as your determinant isn't 0, you're fine. You keep moving forward. Second thing, find my adjoint or adjugate. Once again, I'm focusing on 2 by 2s. It's really basic. If m originally looks like this, my adjoint matrix, I'm going to make these two switch places. So 5 and -3 switch places. And then these two numbers change the sign. So my 1 becomes -1 and my -2 becomes +2. That's it. These two switch places, these two change their sign. Yay, congratulations. That's it. Okay, so now I have my determinant, I have my adjugate, now I can go ahead and do my calculation. So it's 1 over the determinant times my adjoint. This is a scalar times a matrix, so I just follow it through. 3 over 13, 1 over 13, -2 over 13, -5 over 13. A lot of times, you're going to get fractions in your inverse, and that's totally fine. There we go. Let's look at another one. Let's say n. I want to calculate the inverse of n. Same formula. 1 over the determinant of n times n adjoint. First thing, calculate n, the determinant of n. N looks like this. 3, -3, 5, -2. I draw my little fish. 3 times -2 minus -3 times 5. 3 times -2 minus -3 times 5. Do that math, I end up with -6 plus 15, or 9. It's not 0, so we're great. 2, find an adjoint. If n originally looks like this, 3 and -2 are going to switch places. And then the 5 and the -3 are going to change the sign. So my +5 becomes -5, and my -3 becomes +3. There we go. I've got my two pieces. Put them together. N inverse equals 1 over 9. -2, -5, 3, 3. Multiply that through. I get -2 ninths, -5 ninths, 1/3, 1/3. I can double check my work. I can check to see if n times n inverse equals identity. I can check to see if m times m inverse equals identity. You can do that by hand. I would let MATLAB do that. Okay, speaking of MATLAB. In MATLAB, it looks like this. So here's m, here's n. So if I want to find the determinant of a matrix, I would just say DET-M. DET, determinant, I can see that, yep, checked, it's -13. Same thing with n, DET-N. You can't, there's no built-in MATLAB function to find the adjoint or the adjugate, so you can just find the inverse directly. So there's two ways to calculate the inverse. You can say m raised to a -1. That will give you the inverse. Note, your default shows you decimal places. If you want fractions in MATLAB, you can. You can just type format rat. And then you retype your calculation and you can see it gives you the fractions. So format rat, format rational, it gives you rational numbers or fractions. And you can double check your work, which that's what we got. That's what I got. You can also use the inverse function. So INV is the inverse function. So inverse n. Same thing, check your work. And these two things, they work for any size matrix. So you could have A equals rand I, 10, 3 by 5 by 5. It will work in MATLAB. You just don't know how to do it yet on paper. We will get to doing it on paper later on in the semester. Right now, on paper, we are focusing on 2x2 systems. Yeah, but these functions work for any size matrix. Keep in mind, one caveat is it needs to be a square matrix. So you can't say inverse of a non-square matrix. Let's see what it gives you. Yeah, it says matrix must be square. So when you're doing inverse, you're working with square matrices. 2x2 systems on paper, any size square matrix in MATLAB. Okay, that's all fine and dandy. So now let's get to our division operations. So like I said, we're not going to divide in with matrices. What we do is we multiply by the inverse. So there's two types of division in MATLAB. We have right division and left division. And it just depends on the way you have your slash. So right division is backslash, left division is forward slash. If we are doing right division, we are essentially doing this operation. We are saying m times n inverse. If we are doing left division, we are doing this operation, m inverse times n. So the slash, discovered this last lecture, the slash angles towards the one that has the inverse. So here it angles towards n inverse. Here it angles towards m inverse. And like I said, it's just matrix multiplication. So I take m looks like this, 5, -2, 1, -3. And now I can multiply it by n inverse. I can use either this version of n inverse or this version, it doesn't matter. So -2/9, 1/3, -5/9, 1/3. It's a 2×2 times a 2×2. My result is going to be a 2×2. Michael, so the forward slash is right below your backspace on your keyboard. Right above enter. So it's a 2×2, so I just do my dot products. So this one. So I have 5 times -2/9 plus 1 times 1/3. And then this one and this one, so -2 times -2/9 plus -3 times 1/3. And then my other set of dot products. 5 times -5/9 plus 1 times 1/3. -2 times -5/9 plus -3 times 1/3. And you can do that math. So we just find the inverse of n first, use that in our calculation. If we do left divide, it's going to be m inverse times n. So m inverse looks like this. We can use either option. I'm going to use the first one. It's 1/-13 times -3 to -1, 5. Since it's a scalar, we can just pull it out and work with whole numbers. I prefer to work with whole numbers. It's just easier that way. So we can just pull it out separately. It's not gonna change our final answer. And then n looks like this: 3, -3, -5, +5, -2. Same thing. It's just matrix multiplication. 1/-13. I will do that distribution in later. Dot product. -3 times 3 plus -1 times -3. Next one, 2 times 3 plus 5 times -3. Do both of those with my second column. -3 times 5 plus -1 times -2. 2 times 5 plus 5 times -2. Figure out those whole numbers, then you can distribute -13 in. You can always check your answers with MATLAB. M divided by n. There's your answer. It should be the same as m times n inverse, which is the same as m times inverse of n. So these are all the same operation. So you can see that division with matrices is just another form of matrix multiplication. Same thing, m left divide n. If you ever run into this asterisk, it just means that it's practically 0. So it's a really small number. This is the same as m raised to the -1 times n. Or m, or inverse of m, times n. Same thing. So this is just a really small number. It's just 0. That's matrix division. That's it. That's division. So just like I made some supplemental videos on matrix multiplication, I'll also do 2 more examples showing the inverse as well. Yes, so when you see this in MATLAB, you're effectively talking about zeros. Let me see if I can do format. So if you ever want to get rid of these fractions, you just type format again, and it will go back. If you get your, so here it's the same answer, just not with fractions, and we can see that it's 0. It's practically 0. If I wanted more digits, I can type format long, do the same thing, and we can see it's still practically 0. So if you ever see this in format rat, it's indicating that it's a very, 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 very tiny number. It's pretty much 0. It just didn't calculate 0 due to rounding error. Okay. So why do we even care about division? We care about division because the main application for this class is going to be solving systems of equations. Systems of equations. So we are going to focus on this a lot later on in the semester, but I'm going to introduce this idea here. So given a system of equations, you've seen them before. A lot of times you see them like this in your previous algebra courses. They're relatively small, relatively simple. However, as you move up in your academic path, you're going to run into significantly more complicated systems of equations. And the nice thing is that we can use the principles of linear algebra in order to easily solve these equations. So that's what we're going to do. That's what we're going to introduce right now. So given a system of equations, we can write it in the form of what's called AX equals B, where A is going to be filled with our coefficients on our unknowns. X is going to be a vector of unknowns. And then B is also a vector of constants. And these come from your right-hand side of each equation. So like I said, we are dealing with square matrices. So A is going to be a square matrix. X is going to be a vector, and B is going to be a vector. So if we write things in the form of AX equals B, it turns out the solution is going to be A inverse times B. Where here we go. That's my key piece in linear algebra, is if I write it in the form of a matrix, this is my one line to solve it, which, as we know, this is the same as saying A left divide B. So I can solve an entire system of equations by doing one matrix multiplication versus having to do a bunch of substitutions or elimination steps. Okay, so given this system, let's go ahead and write it in the form of AX equals B. So like I said, A is going to be our coefficients of unknowns. If I look at this system, I have 2 equations and 2 unknowns. My unknowns are X and Y. And for our purposes right now, it's always going to be 2 and 2, 3 and 3, 4 and 4, 5 and 5, 6 and 6, 7 and 7, 20 and 20, etc. It's always going to be the same number of equations for unknowns because right now A needs to be square. There are caveats to this, but we will get to that later. So to set up A, I'm going to draw my square matrix. The first row in A is going to come from the values from equation 1. The second row in A is going to come from the values in equation 2. The first column in A is going to come from my first unknown, or X. The second column is going to come from my second unknown, or Y. And it doesn't matter the order. I could do y and x. That doesn't matter. So here's A. So looking at this system here, from equation 1, the number in front of x is -2. The number in front of y is 1. From this second equation, the number in front of x is 4. The number in front of y is 1. Okay, so it matches my grid. Equation 1, unknown 1. Equation 2, unknown 2. So your equations can be written and rearranged in any way they want, as long as when you are writing it in your A matrix form, you keep this grid system in place. There's A. X, my x vector in AX equals B, is my vector of unknowns. It's going to be just full of letters. X and Y. So don't get confused with this X and this X. They're two different X's that represent two different things. This X is an unknown in my system. This is my unknown in my matrix form. These can be named whatever you want. It could be X1, X2. Could be XYZ, ABC, whatever. It's just letters. Turns out it doesn't matter what those letters are. But note the order of X and Y here matches this order. So essentially I just copied and pasted these down. So if column 1 corresponds to X, that means X needs to be first here. If I multiply these two matrices together, I'm going to end up with a 2-by-1 system where I get -2x plus y and 4x plus y. Notice that matches this. Okay, so there's A and there's X. Now I need B. B is also a vector. It's going to be the same number of equations, where the first number comes from equation 1, second number comes from equation 2. It's just the constant on your right-hand side. So from equation 1, it's 5. From equation 2, it's -2. Ta-da! There we go. We have it in the form of AX equals B. To solve this, X equals A inverse B. So I'm going to find A inverse. A inverse, 1 over the determinant of A times A adjoint. The determinant of A is going to be -2 times 1 minus 4 times 1. -2 times 1 minus 4 times 1. Or -6. My adjoint is going to be 1 and 2 change places. 1 and -2 change places. 1 and 4 get the sign flipped. So X equals 1 over -6, 1, 4, -4, -1, -2 times B. B is just this, 5, -2. That's just a matrix multiplication. Equals 1 over -6, dot product. 1 times 5 plus -1 times -2. Dot product. -4 times 5 plus -2 times -2. X equals 5 minus 2. 5 plus 2. 7. -20 plus 4. -16. Multiply that through. Hold on. Ryan, right? I called you Ben earlier. I had 2 Floras last semester. 7 over -6. 16 over 6. Simplify that. I get 7 over -6. 8 over 3. So Ryan says, if we use MATLAB to solve the system equations, so if it's a 2x2 and you are asked to solve it by hand, yes, you need to solve it by hand. Everything, just like I showed you. If it's bigger than a 2x2, you can't solve it by hand right now. You can always use MATLAB to check your answers, though. Okay. So there we go. There's my solution. X equals 7, negative 7, 6, and 8/3. That means that this x equals xy. It equals this vector, where my first unknown is this one, and my second unknown is this one. So x equals 7, negative 7, 6, y equals 8/3. There we go. I have just solved the system of equations, doing some pretty more straightforward calculations. I mean, for a 2x2, it's pretty simple. You can easily do it using substitution. But as we get to bigger and bigger matrices, it's going to be much more complicated. So in MATLAB, if I wanted to solve this, I would just type it like this. A is there, B is there, X is solved for. So keep in mind, MATLAB will not, let me do format right again. MATLAB will not convert your system equations into matrix form. You need to know how to do it. You need to know how to construct A. You need to know how to construct B. We don't type X equals. I don't ever type X equals X, Y into MATLAB. That doesn't make any sense to MATLAB because it doesn't know what X and Y are. Instead, we solve for X by saying A inverse times B, or inverse A times B, or A left divide B. And we can see our answer is 7, 6, and 8/3. That means X, my unknown X in my equation is negative 7, 6. My unknown Y in my equation is 8/3. So don't worry about that right now, Michael. Do you have any challenge activities corresponding to that? I mean, it probably introduces, but you don't have to solve any problems. Ignore that. We will learn how to do it later on in the semester. For the participation activities, I mean, you can click to get the right answer. Okay. So if you're trying to do row operations to find the inverse of something bigger than a 2x2, just click show answer. I mean, you can try it if you want. You can always use MATLAB to do it. But we will get to that later on in the semester. I completely forgot it does 3x3s. Okay. Okay. What do we have? Okay, we've got time. So, like I said, I will put together another video going through 2 more examples showing that, going through all of the steps, finding the inverse, solving a system, all that fun stuff. I will post that later today. But what I want to make sure I get to is solving a system of equations that's bigger than a 2x2. So we can do a 2x2 by hand, just the ways I just showed you. What if our system of equations was bigger? So here I have 4 equations and 4 unknowns. We know how to do it in MATLAB. It's just A, or X equals A inverse B, or A left divide B, or inverse AB. It's the same operation in MATLAB. We just need to know how to set up A and how to set up B. So if you have more than 2 equations, more than 2 unknowns, we're still going to set up A the same way. So for this one, I have 4 equations, 4 unknowns. My unknowns are I1, I2, I3, and I4. Those of you who are in EAS 200 or have taken it, this system of equations came from a nodal analysis on a circuit. So this is an example of, as we get to more complicated material in our academic path as engineers, we're going to run into more complicated sets of equations. Okay, so my unknowns are I1, I2, I3, and I4. However, A is still set up the same way. So it's a 4x4, where I have 4 rows. Each row corresponds to an equation. Equation 1, equation 2, equation 3, and equation 4. My columns in A correspond to my unknowns, I1, I2, I3, and I4. And I just fill it in. So for equation 1, my value in front of I1 is 32. My value in front of I2 is negative 16. I3 and I4 don't show up in this equation. If they don't show up in an equation, that doesn't mean they're not there. It just means the coefficients are 0. So there's my first equation. Second equation, negative 6, 42, negative 12, negative 14. So keep in mind, you just need to make sure you're doing the right unknown in the right spot. This equation could have been written differently. It could have been written as negative 6 I1 minus 12 I3 minus 14 I4 plus 42 I2. These coefficients would still go in the same order because you need to match the column. I1, I2, I3, I4. Otherwise, you will get the wrong answer. Okay, for equation 3, I have 0 because I1 doesn't show up, then negative 12, then 24, and negative 4. For equation 4, same thing, I1 doesn't show up, so it's 0. Then we have negative 14, negative 4, and 23. That's A. I set up my grid. Equations, unknowns. X. X is full of my unknowns. I just copy and paste these down. I1, I2, I3, I4. It needs to be in the same order. And then B. B is one of my favorite ones to construct because it's pretty straightforward. It's just your constants on your right-hand side. For this system, it's going to be negative 28, 0, 36, negative 42, in that order. So equation 1, equation 2, equation 3, equation 4, negative 28, 0, 36, negative 42. Okay, on paper, we have wrote AX equals B. Written, we have written, wrote, written, past tense of write for this context. Yay, English. In MATLAB, we're going to type in A. It just so happens instead of A being a 2x2, now it's just a 4x4. So here's what A looks like. B, same thing. We just type in B. Instead of it being a 2x1 vector, it's now a 4x1 vector. And then to solve for our unknowns, to solve for all of my currents, to solve for all of my I values, I say I equals A left divide B. For this one, it doesn't really make sense to have our rationals, so I'll just go back to format, retype it, and we can see all of my currents. So now there's my solution. I1 is my first unknown, negative 1.1778. I2 is negative 0.6055. And I3, 0.8563. And I4 is negative 2.0457. There we go. For the 2x2, it didn't really save us that much time, but for this 4x4, I'm not gonna lie, it's much simpler to do it this way. I could have done x equals A, left divide B, but honestly, I can just name my variable whatever I want. I went with I because it's full of currents. Okay, let's do one more. One more. Here we go. So here's a system of equations developed from a truss structure in statics. So once again, it's close to home, those of you guys who are in statics or have taken statics or are going to take statics. Here I have 1, 2, 3, 4, 5, 6, 7 equations, which means I should have 7 unknowns. My unknowns are F1, F2, all the way to F7. A is set up the same way. Equation 1, 2, 3, 4, 5, 6, 7. F1, F2, F3, F4, F5, F6, F7. My first equation, F1 has a cosine 30 in front of it. You don't even need to change it. Just say cosine 30. F2 has a 1 in front of it. There's no other unknowns, so the rest of them are just 0. For equation 2, F1 contains a sine 30. There's nothing else, so the rest are 0. Equation 3, I have negative cos 30 in front of F1, negative cos 60 in front of F3, cos 60 in front of F5, and a cos 30 in front of F6. The rest of them are 0. Yeah, I know, Chaz. When I type it into MATLAB, I would definitely use the D for cos D, sine D. But when I'm typing it out on paper, I can see what it is, so I don't need to write that extra letter. But yes, these are all degrees, so we'd use the appropriate function in MATLAB. And then you would continue for 4, 5, 6, 7. We're out of time, so I'm gonna hurry up. My X is full of my unknowns, F1 all the way through F7. B is my coefficients, or my constants on my right-hand side. 3,000, negative 6,467, negative 3,000, 0, 0, negative 75, 33, 0. Plug those in. As some of you guys know, this would probably take quite a bit to solve by hand, going through your substitution and all of that fun stuff, as you would have to do in statics. But if we write it in the form of ax equals b, we can just go to MATLAB. We can type in A. There we go. That's what it looks like. So one strategy in typing in A, note, one, I used the D for cos D and sine D in order to make sure I'm in degrees, but I also aligned my numbers. I just put more spaces so that things matched up a lot clearer to what I would see it on paper. So here's my first column, second column, third column. So these are my first equation, second equation, third equation. And just because it doesn't matter how many spaces there are between numbers, but I can use spaces in order to help align things, make things much clearer. So I type in A, I type in B, and then same thing, F equals A left divide B. And now I can see all of my answers. If you ever run into something like this, where you get 1 times 10 to the 4th times everything, you can just do format short G, and it will adjust. It does this because there's a wide variation between your numbers. Some are on the scale of 10,000, some of them are on the scale of 1,000. So it's just because of the range. But if you do format short G, it will get rid of that and type out the numbers. But there we go. So if we write an equation in the form ax equals b, it doesn't matter how big it is, it's still going to be 3 lines of code. Type in A, type in B, A left divide B. I wanted to show you that because in your homework you have like a 17 by 17, something ridiculously large. So I wanted to focus on that. I will post a video showing more examples later today. So you guys can use those as a reference in order to get more examples on finding the inverse of a 2x2 and solving a system of equations, because you will need to know how to do it by hand. Other than that, though, we are done for today. Final questions. I just want to commend you guys. You guys have been doing great. I have never had this much participation before in lecture, even in assignments. So keep going, one thing at a time. Just keep going. Good job. Yeah. Final questions. Other than that, we are done, and I will see y'all next week. Enjoy your lunch or breakfast. Not yet. Homework 2 should have been graded. I'm pretty sure someone forgot to grade some of my sections though. So they should be updated soon.